to start recording, and if there aren't any questions right now, we'll go ahead to screen sharing like we usually do, but if you think of anything later, make sure you bring it up. And beginning today, and really for the rest of the semester, we're going to talk about ecology from a broader perspective. So we're going to begin by looking at biogeography. And biogeography studies the distribution of living organisms around the Earth on a large scale. So not seeing, where the habitat of red-winged blackbirds is or stone roller minnows, but looking at it more in terms of which continents do we find certain animals on, which oceans do we find certain things in. And one of the things we see is that historically a major factor that has shaped biogeography is a process called continental drift. Now, if you're like me, and I don't know if I was just a nerd when I was a little kid, but one of the things I noticed when I was a little kid, it was if you look at South America and Africa, they seem to fit together like two pieces of a puzzle. South America has that part that juts out. Africa has an indentation. It seems like they kind of fit together. And back in the 1950s, a geologist named Alfred Wegener came up with his ideas about continental drift. And at the time, they were really a hypothesis, but today we talk about the theory of continental drift. So remember, in science, when we call something a theory, this means that we actually have a lot of evidence to support it, that it's a hypothesis that's been tested and it's never really been disproven or rejected. So we want to keep that in mind. Now, with continental drift, we can't do an experiment to see if the continents are moving. So that's not possible. But remember, when we come up with a hypothesis, you can make predictions from that hypothesis. And continental drift does lead to a number of predictions that we can test in experiments. And we can't reject the hypothesis on the basis of those predictions. They seem to be correct. For instance, if we look at South America and Africa, one of the things that before continental drift was proposed, one of the things that really baffled biologists was, why do we have a lot of animals and a lot of fossils on the east coast of South America, the Atlantic side, that are very closely related to organisms on the west coast or the Atlantic side of Africa? We've got the whole Atlantic Ocean between them. So shouldn't there be some pretty significant differences? But it turns out that continental drift can explain this. Starting about probably 335 million years ago or so, all the land masses that we currently see were together. They formed a large, what was called or what we call now a supercontinent, Pangaea. And you can see the outlines of some of the modern continents here. Australia was kind of stuck off to the side. Next to that was Antarctica. Next to that was India. Then we have Africa in here, Asia in here, North America. I'm sorry, I said Asia. We have Africa here. We have South America here. Then we have North America. And then up here we have Europe and Asia and the Middle East. And what happened was somewhere around 225 million years ago, Pangaea began to break up as continental drift pushed these continents apart. And by the time we got to about 180 million years ago, the continents were so far apart, they weren't really considered to be a supercontinent anymore. They were divided into two large continents. One was called Laurasia, and you can probably tell by the name that Laurasia included Asia, but it also included Europe and the area that today we would call the Middle East, and also North America. And the second continent was Gondwanaland. And Gondwanaland was the southern continents, South America, Africa, Antarctica, Australia, and then this blob here is actually India. So gradually the continents moved further and further apart until they came to their modern day positions. Now, how do they move? This is where Wegener's theory comes into play. Even before Wegener's theory, we knew that there are three basic layers in the Earth. There's an outer layer called the crust, and this is what we tend to think of as the soil, the ground that we live on. There's a very inner layer that's full of molten metal called the core. And in between them, there's an area called the mantle. And the mantle is heated by the core. So the mantle is liquid. And even though it's heavy rocks and minerals, there are currents in the mantle. And what we see is that pieces of the crust float on this mantle, and they move with the currents in the mantle. Now, these pieces of the crust are called tectonic plates. And you may have heard of some of these. This is one of the reasons why places like California have so many earthquakes. California is actually located on a plate that's separating from the rest of the 48 contiguous states. If we look around the Pacific, there's an area around the Pacific, and it extends down the western border of North America and South America. There's an area that's sometimes called the Ring of Fire, where we see a lot of volcanoes and a lot of earthquakes. And this Ring of Fire basically corresponds to the boundaries between tectonic plates. So these tectonic plates are constantly shifting due to a couple of factors that we'll talk about in a moment. These shifts are very small, but they can actually be measured. For example, if we look at North America and Europe, notice they start out very close together and they're gradually moving further apart. And we can actually measure that they're moving farther apart by about 2.5 centimeters, which is about an inch a year. Now, how do they move apart? Because in the middle of the Atlantic, there are some plates that meet. Now, we could have land over these tectonic plates, but we could also just have water. And where these plates meet, what we see is there's actually an active range of volcanoes in the middle of the Atlantic Ocean. It's called the Mid-Atlantic Range. We don't really experience these volcanoes much because they're underwater for the most part. So we don't really see them. But these volcanoes are constantly erupting. And there's, I guess one way to think about it would be a crack in the middle of the Atlantic Ocean where these plates are separating. And some of this hot molten material, it's called magma, is coming up from the center of the Atlantic Ocean. And the Mid-Atlantic Ridge was actually discovered back in the mid-1800s. At that time, we didn't know about plate tectonics, but when they were doing studies to figure out where they could lay the transatlantic cables to communicate between North America and Europe, they began to discover some of these mountain ranges under the ocean. Now, as I say, we don't see most of these mountain ranges, but up in the northern part of the Atlantic, these mountain ranges, the volcanoes in them have erupted so much that they've actually created islands that stick above the surface of the water. So this is one reason why, if you've read anything about Iceland, Iceland actually has a lot of active volcanoes and they have earthquakes. Why do they have all this? Well, because it's really on this Mid-Atlantic Ridge. It's a part of the ridge that sticks up out of the ocean. And we have similar spreading going out throughout the world. If we look in the Pacific, this is how the Hawaiian Islands were created. And you can actually trace the Hawaiian Islands by looking at where the volcanic activity that created them is underwater. And the oldest islands are farthest away from this because the movement of the plate has separated it. And the younger Hawaiian islands are right over the volcanoes right now. Now, the longer something stays over a particular volcano, the bigger that landmass gets. If it moves over it somewhat slowly, then it might only be a small island, or it might not even ever reach the surface of the water. It might be in what's called an underwater seamount. So the continents are constantly moving. But one of the things this means, if we go back to the Permian period, the Permian was the beginning of what's sometimes called the age of reptiles. And during the Permian period, dinosaurs started to evolve. But if we look on Pangaea, one of the things that we see is that the same species of dinosaurs tend to be found all over Pangaea. Now, by the second period of the age of reptiles, something called the Triassic period, notice that the continents are starting to separate. And during the Triassic period, one of the things that we see is that these reptiles, including some of the first dinosaurs where we used to have the same species all the way across Pangaea, now they're in different environments, so divergent evolution starts to happen. We start to get different species in these different areas. And the other thing we can see from this, notice that Australia has always been kind of out here on its own. It's just barely connected to the rest of the land masses in the world. And Australia, along with what's now Antarctica, separate from most of the rest of the world pretty early. And this is one of the reasons why today, if you go to Australia, at least until Europeans got there, there were no placental mammals in Australia. All the mammals were marsupials. Now, we have fossil evidence that there were marsupials in Antarctica as well, but Antarctica is too cold now. We don't really have any mammals that are native to Antarctica at this point. But notice that the other thing that's connected at the other end of Antarctica is South America. And if we look at South America is also where we find marsupials, although mostly we find fossil marsupials. And the reason we find fossil marsupials in South America is, notice that recently in history, South America and North America have moved closer to each other. And as they've moved closer and the plates press up against each other, when they press up against each other, it's kind of like pushing your hands against each other. They go upward. So this has created a chain of land. And this chain of land that connects North America and South America is Central America. Notice that Mexico was here before. You can see Mexico kind of sticking down here. And this is why Mexico is geographically considered part of North America, not Central America. Culturally, Mexico may be closer to Central America, but geographically, it's considered to be part of North America. Now, what happened when we formed this land bridge between North America and South America? Well, when we formed this land bridge, animals from North America could migrate to South America and vice versa. And North America had mostly placental mammals. And when these placental mammals crossed this land bridge and went through Central America down to South America, and keep in mind, we're talking about a process that may have taken hundreds of thousands or millions of years as population shifted. But when placental mammals invaded South America, something that we talked about a few days ago happened: competitive exclusion. Placental mammals are much more efficient than marsupials at reproduction, having the embryo develop attached to the mother's uterus the whole time instead of only about a third of the time, and a third of the time, 2/3 of the time in the pouch, like marsupials do. having the embryo develop in the uterus is advantageous. Development is faster, the embryo is more protected. So basically, placental mammals outcompeted marsupials in South America until most of the marsupials went extinct. So we can understand a lot about where organisms are found by looking at the history of the continents. And as I mentioned before, it also explains a lot about what we see in the fossil record. Why should we find similar fossils in South America and Australia and Antarctica? Now notice the other thing we can see with continental drift, not strictly related to biology, but it does ultimately affect the distribution of organisms. This little triangle here that kind of breaks off from the southern continents very early, this is India. And notice that India drifts northward and basically collides with Asia, where we have this little indentation here. And because these two plates collide, and because they're pushing up against each other, this forms mountain ranges. So this is where we have the Himalayan mountains, the highest mountains in the world, because India is moving northward. It's pushing into Asia. So again, when they push together, they force the land up in this region. Now, we talked about the mid-Atlantic ridges, and we talked about, you know, a collision of land masses here. Both of these areas tend to make mountains, but we also have some areas called subduction zones. And in subduction zones, we have two plates next to each other, and one plate kind of dives under the other plate. It goes back into the mantle. So this causes, notice that would cause one of these plates, the one that's diving under the other, going back into the mantle. This causes the plates to get smaller. So we can have activities that move the plates farther apart. We can have activities that move them closer together. So both of these factors are important when we look at history. And keep in mind that plate tectonics is still going on today. As I mentioned, when we measure the Atlantic Ocean, it's getting a little bit over an inch wider every year. So, you know, you don't have to worry that it's going to take a longer plane flight or a longer cruise to get to Europe during your lifetime. But in another million or 100 million years, the basic shape of the continents could look different than it does now. So we want to keep that in mind. So continental drift is now a theory. There's so much evidence to support it. We're positive it happened. It's no longer a guess. Now, if we look at the location of the continents today, there are 6 basic biological, they're usually called realms, on the Earth. And keep in mind that these realms were named by the Europeans, so you kind of have to put yourself in the mind of the Europeans back in the day of Christopher Columbus and other explorers who were traveling around the world. Well, when the Europeans start exploring the world, they don't know much about Asia, but Marco Polo has been to Asia. They don't know much about Africa, but there are people who have been to Africa. So Africa and Asia and Europe are the old world, the world that Europeans are familiar with. So when we look at Africa, the organisms that live in this area, this is called the paleotropical realm. Paleo means old. If we look at Europe and most of Asia, north of India, this is called the Paleo-Arctic area, even though a lot of that is not what we would think of as an Arctic climate. If we look at the Middle East and India and Southeast Asia, this is what was called the Oriental realm. And again, we might not think of India or the Middle East as being Oriental. Australia and some of the large islands like New Zealand and Tasmania and New Guinea that are in that area, this is logically enough the Australian realm. Now, notice that South America, the equator is this line right through the middle in all these drawings. Notice that a lot of South America is tropical, and so is most of Mexico and Central America. So this area is called the neotropical. Neo is new. So this is the new tropics, because remember, the New World to the Europeans was the Americas. North America is the neo-Arctic. So we have the Paleoarctic, the neo-Arctic, the Paleotropical, the neotropical, and then we have the Oriental and the Australian. Notice there are very few living organisms on Antarctica, so the Europeans didn't bother to give that a name. And although we find lots of fossils, and notice if we go back to some of our original drawings, at one point, Antarctica was in much warmer climates. Similarly, we actually have evidence by looking at fossils that at one point the Sahara Desert was a lush forest. So things can change pretty dramatically. Now, continental drift happens on such a long, slow time scale that it's not really something, as I say, that's going to change during our lifetime. But there are a couple of factors that affect the types of living organisms that we see in any area during our lifetime. So let's think about one of the most important, which is solar radiation. So here we have some yellow bars showing sunlight coming into the earth. And here's one of the things that we want to focus on with this, because this is really the key to this diagram. Think about the length of this line where the bar hits. Notice that solar radiation that hits near the equator, this line is a shorter line than when the solar radiation hits further away from the equator, where it's hitting more on the curvature, and it hits an even larger area. That line is longer when we look at the poles. Now, this is important for one main reason. When we look at sunlight hitting the equator, the same amount of solar energy is concentrated in a small region. Think about the length of that line. As we move towards the poles, that same amount of solar energy gets spread out over a larger area, over a larger surface of the Earth. That line is longer, both at the North Pole and the South Pole. So this means that if we look at a fixed unit of area, say we look at a square mile or a square meter, regions near the equator receive more solar energy per square meter than regions near the poles. In fact, they receive about 2.5 times more energy. Now, this drawing is a little bit deceptive because we have to keep in mind that if we look at the Earth and we compare it to the sun, the north-south axis of the Earth is actually tilted a little bit compared to the direction that solar radiation is coming in. So the fact that we have direct sunlight hitting a smaller area near the equator, a bigger area near the poles, this means that no matter what, the climate near the poles, the North Pole and the South Pole, that climate is going to be colder than the climate near the equator. And that's simply because of the amount of solar radiation per unit area, per square meter or per square kilometer or per square mile, however you want to think of it. More solar radiation, the equator would be warmer. But there's another factor as well. The north-south axis of the Earth is slightly tilted. And since it's slightly tilted, this means that sometimes the North Pole is tilted towards the sun, sometimes the South Pole is tilted towards the sun. Imagine taking our model of half of the Earth here and rotating it about 23 degrees here. So when the North Pole is tilted towards the sun, this is when the Northern Hemisphere has summer. When the South Pole is tilted towards the sun, this is when the Southern Hemisphere has summer. So the Earth is actually a little farther away from the sun during our summer, the Northern Hemisphere summer, and it's a little bit closer to the sun during the Southern Hemisphere summer. So some people think summer happens when the Earth is closer to the sun. It actually happens when the North axis, the North Pole, is tilted towards the sun, or the South Pole. So for people in the Southern Hemisphere, this is why they're having their winter as we're having summer. So we're in spring, getting close to summer. They're in fall right now in the Southern Hemisphere, getting close to winter. And it's because of this tilt of the Earth's axis. Notice if the Earth's axis wasn't tilted compared to the sun, there would be no seasons. Areas near the equator would still be warmer because they get more solar energy per square kilometer, but there wouldn't be any difference as the year went on if the Earth's axis wasn't tilted. So the tilt of the Earth's axis creates the seasons. Now, this solar radiation does a couple of things. I mean, the thing that we notice the most probably is that, it's warmer in summer, it's colder in winter. But a lot of the things that are warm and cold, we don't notice that much. Solar radiation doesn't just heat the land, it also heats the water and the air. And when water and air are heated, they expand. And when they expand, one of the things that we see is that they're less dense. Now, air near the poles where they don't receive as much direct radiation, that air cools down. And when air and water cool down, they're denser. So we have dense air when it's cold, or water. We have less dense air when it's warm, or water. So why does that matter? Well, when we have dense air or dense water, it tends to flow towards less dense air and less dense water. Think about back in 105 when we talked about diffusion. In diffusion, things move from a high concentration to a low concentration. Density is, in a way, another way of looking at concentration. So things are going to move from more dense areas to less dense areas. So water moves from where it's denser, colder, to where it's less dense, warmer. Air moves from where it's denser, colder, to where it's less dense, warmer. So what happens because of this? Well, two things. If we look at the oceans, what we see is that in the oceans, the major currents are created by the movement of water according to its density. Notice that less dense water is shown here, mostly in the red, the warmer. And notice that the less dense water is typically located near the equator, or when it's further away from the equator, we can see lines showing that this less dense, warmer water came from near the equator. The denser water is located mostly in the Antarctic Ocean and then moves north, or in the Arctic Ocean and it moves south. Now notice these climates that we see around the Earth are often strongly influenced by these ocean currents. If we look down here, there's something called the Gulf Stream. And if we look at this Gulf Stream, which is haha, in the Gulf of Mexico, surprise, surprise. Notice that part of the Gulf Stream branches off and goes north along the east coast of the United States. And then it actually continues to flow all the way north until it reaches England and parts of Europe. At that point, some more splits off and goes even further north. Now, notice that this Gulf Stream is carrying warm water from the Gulf of Mexico. So this warm water, if we look at the eastern coast of the United States, the eastern coast of the United States is probably warmer than it would be without the Gulf Stream. And if we see that the Gulf Stream carries this warm water up towards England, France, Germany, Europe is much warmer than it would be without the Gulf Stream. Notice if we look at England, the United Kingdom here, these little islands, look at how far north this is. The United Kingdom, England, is as far north as Canada. It's as far north as southern Alaska. The climate in England is not as cold as it is in Alaska or Canada. Why? Because of this warm Gulf Stream carrying water in that direction. So that's very important in terms of determining the climate of Europe. It's important in other areas as well. And some of these climates, some of these currents have a big effect on our weather. You've probably heard of El Nino and maybe El Nina as well. These are currents out in the Pacific. And depending on whether it's an El Nino year or an El Nina year, sometimes it's neither, we have unusually warm winters or unusually cold winters. So we want to keep these currents in mind. Now, the other thing that happens, partly because of the uneven heating of the Earth, in this case of the air, and also partly because of the rotation of the Earth, is this creates the main air currents that we see. So what we see as we go around the world is we see alternating bands where the wind either comes from the east or the wind comes from the west. And we see areas where we have warm air and cold air replacing one another. So if we look at this map of the United States is up here, and if we look at where we are in Chicago, right in this area, notice that our main winds are coming from a westerly direction. They start in the west and blow east. When we say that a wind is a westerly, it's actually blowing east. That means it starts in the west. So, you know, as I'm sure you've noticed, if you've ever actually watched a weather forecast on TV, not just, you know, read it on your phone or your tablet or whatever, what do they talk about when they talk about what type of weather we're going to get next? They're always looking to the west of Chicago. They're looking at Des Moines or Minneapolis or maybe Kansas City. It depends, because sometimes our winds are coming from the northwest. If they're coming from the northwest, that would be more Minneapolis. If they're coming from the southwest, that would be more Kansas City. If they're coming more directly west, then it would be Des Moines or Omaha if we go a little bit further west than that. So we can predict our weather fairly well based on knowing what direction the major winds are blowing. And if you've ever seen any of those maps they show of the jet stream is always moving from the west to the east, at least in this part of the world. Keep in mind, if you look at these, you notice that the directions vary in different parts of the world. So we want to keep that in mind. Notice you can also see some of the things that early settlers noticed. When the Europeans were trying to explore the Americas, one of the things they encountered was depending on what route they were taking. If they were at about 30 degrees north, they encountered something called the horse latitudes. And the horse latitudes were named because the winds weren't very good there. Well, notice you can see why. If they're right around 30 degrees north, some of the winds are blowing north, some of the winds are blowing south. So they're in an area of relative calm in between these two prevailing winds. So they were named the horse latitudes because when the Europeans came to North America, they brought horses with them in many cases. And if they got stuck in these areas, they would throw the horses overboard. So they would lighten their load so that hopefully the light wind would still help the sailboats. So when the winds blow in these directions, this also creates some of the patterns of precipitation that we see. Because if we look at warm air can hold a lot of moisture. So it can hold more water for precipitation. Cold air tends to not hold as much moisture. So there's less moisture for precipitation. Now, to pick up moisture though, how does the moisture get in the air, regardless of how much it can hold? Well, the air has to move over water. So this means if we look at air right after it moves over water, it tends to have a lot of water, so there can be a lot of precipitation. If you look at the United States, the middle part of the United States is the Great Plains. And the Great Plains is an area where there's not that much precipitation. Well, notice if you're in the middle of the Great Plains, basically from Illinois to the eastern border of the Rocky Mountains, if we look in that region, you're not very close to the Pacific Ocean or Atlantic Ocean or the Gulf of Mexico. So there's not a lot of precipitation in that area. Grasses don't require a lot of water to grow compared to trees and bushes. So the Great Plains, or what's sometimes called the American prairie, those were the plants that grew there because of lack of moisture. Now, this is affected by local geography as well as just how close an area is to an ocean. So let's look at what we see in the Western United States. So the blue over here represents our Pacific Ocean. And if we look at really all the way from South America up to Alaska, there are mountain ranges, not very far inland. They're sometimes collectively grouped together and called the coastal ranges. But in South America, they're the Andes, there's the Sierra Nevadas. They have different names in different places. So if we look at this part of the world, the prevailing winds are coming from the west. And they're coming off the Pacific Ocean. So this is very warm, moist air. It's got a lot of water vapor in it. As the air goes up the mountainsides, and you might not think of air as having to go up, but it does. As the air goes up these mountainsides, it cools. Now remember what we said, cool air can hold less moisture than warm air. So as it goes up the mountainsides and the air cools, there's a lot of precipitation. There's a lot of precipitation on the western side of those mountain ranges that are located in North America and South America. But by the time the air rises to the top of the mountains and starts to go down the other side, most of the moisture that was in it has been lost. It's fallen out as rain or at the upper elevations, maybe snow. So as a result, when we go down the eastern slope of these mountains, this eastern slope only gets dry air, and the eastern slope tends to form deserts. We sometimes say that the eastern slope forms what's called a rain shadow. Just like in a regular shadow, there's no sun. In a rain shadow, there's very little rain. So if we look at some of the effects of this, if you look at the Western United States and you look on the western slopes of some of those mountain ranges, in Washington and parts of Oregon, this is where we have what's sometimes called the temperate rainforest. If you know anybody who lives in this area on the western slopes of the mountains in Washington and Oregon, they get maybe 100 inches of rain a year. Now, how much rain is that? Chicago averages about 33 inches of rain. So that's 3 times as much rain as we get. So some people don't like places like Seattle because they complain that, there are too many cloudy days. So not only do we have a temperate rainforest in the Oregon and Washington area, but if we go down into California, we see some of the biggest, oldest trees that exist. There are redwoods and sequoias. And if we look at these, some of these trees reach 200 feet tall. Some of them are several thousand years old. They're also a good example of how politics often plays a role in environmental science. Years ago, Ronald Reagan was the governor of California, and the sequoias and redwoods out there are protected. When Reagan was governor, he signed an order in the middle of the night so that nobody could stop it, allowing logging companies to go in and cut down some of the sequoias and redwoods. Now, that's not how they demonstrate the interaction between politics and environmental science. The interaction is demonstrated because we had a textbook, and our textbook at the time, went into all the details of how Reagan had signed this bill and, all the shenanigans that happened in the middle of the night to avoid environmental groups. A few years later, Reagan was elected president of the country. What do you think happened to that part of the textbook? Amazingly, it got left out of the next edition. It wasn't in there anymore. So, even in science, where you might think that data rules, it's still subject to, politics and trends and fashions. So in the Western United States, on the eastern side of the mountains, we see deserts. So you might have heard of a place called the Napa Valley or the Imperial Valley in California. And these are very rich agricultural regions. They're actually on the eastern side of the mountain ranges, and they're actually deserts. They're deserts according to nature. Deserts typically are defined as getting less than 10 inches of rain a year, about 25 centimeters. But when humans came along, what humans did was they diverted water from the Colorado River and used it for irrigation in these areas, as well as some other rivers at the northern end of California have been diverted. We've transformed what used to be a desert into a good agricultural environment. The problem is from a pure environmental standpoint, it takes so much water and so much fertilizer and so much energy to grow plants in these areas. It's not really environmentally or maybe even economically feasible. It's feasible for the farmers who live there because they receive large subsidies from the government to grow their crops. But without those subsidies, if they actually had to pay for all their water and for all the things that essentially are provided by the government, they might not be able to break even because it's just not a good environment. Now notice you can see the same thing if you look at where we're located. Think about the amount of snow that we get in the winter. Now notice that we're kind of to the south, but we're also kind of on the western edge of the Great Lakes. And again, the wind in this area blows from the west towards the east. So if you go across the Great Lakes, so think about the air that's in Chicago, as it moves across the Great Lakes, the air that we see in Chicago has just come across the Great Plains. So it's lost a lot of its moisture. But as it moves across the Great Lakes, the air that's in Chicago picks up more and more moisture. So if you've never noticed, pay attention next winter and look at the weather reports further east. One of the best examples is a city called Buffalo, which is on the east end of the Great Lakes. Buffalo typically gets 2 or 3 times, sometimes more, snow than we get here in Chicago. Why? Because we're on the western end of the Great Lakes. The air that hits us is relatively dry. Buffalo is on the eastern end of the Great Lakes. The air that hits Buffalo is relatively moist. It's got a lot more water to drop as snow. The other thing to keep in mind is because of human interventions, like I mentioned, diverting the Colorado River, because of human interventions, there have been dramatic shifts in some of the ecosystems and biomes in the world. We'll talk about some of these more, but if you look at the Colorado River, which starts up in Colorado, if you look at the Colorado River, this is the river that carved out the Grand Canyon. It's a pretty large river. The Colorado River at this time in history doesn't reach the ocean most of the time. Why doesn't it reach the ocean? Because people take so much water out of the Colorado River, it runs dry before it hits the ocean. And the Western states actually have some very complicated treaties that kind of ration how much water each area can take out of the Colorado River. In fact, it just changed a few years ago, but in Colorado itself, the state, it used to be illegal to shovel snow off your roof in the winter. If you got a lot of snow on your roof, you had to let it sit till spring. And the reason you couldn't shovel snow off your roof was because it might be your roof, but that snow, that water was promised to other states. And if all that water melts at once, they can collect their water more easily than if you shovel it off and it melts a little bit at a time during a warm spell in the winter. So the fact that humans use so much of some of these resources has led not only to some unusual environmental conditions, but some unusual legal conditions. You know, imagine getting sued for shoveling snow off your roof. I don't know if I want to get up on the roof and shovel snow in the middle of winter, but if you want to, it seems like you should be able to. Are there any questions about these factors so far? We still have one more to talk about, but we're about out of time, so I think we're going to wait till tomorrow to start that. So if you don't have any questions, we'll stop for now talking about the environment, and we'll continue again tomorrow, or Wednesday, I guess. Any questions before we leave?